Swayam Prabha. Digital India. Educated India.
Hi, so welcome back. We spoke about the K omega, K epsilon turbulence models, right? And the Reynolds average Navier-Stokes equations. Essentially, these are things that you kind of choose these models when you're using a commercial software like ANSYS, right? You go and choose a K omega turbulence model, K epsilon turbulence model. So I try to give you an overview of what this is all about, right? And we also kind of basically an overview and also the Spelett-Alamaras model, right? So there's and we looked at now what we were trying to do is essentially say that now that we are inching towards this, what exactly is computational fluid dynamics, so CFD. So I just started out by giving you some basic formulae for the derivatives, and what we'll do today is to sort of take that basic equation and and what does it mean that I'm going to solve it using CFD, right? So we're going to set it up and see what it means. When I say I'm going to do this using CFD, so the ANSYS, where you just press buttons, where there's an entire code behind it, right, which runs, and people have written that. So what exactly have they written? How have they written? So that's something. I'll give you a little bit of an overview on that. I'm no expert in CFD, but just a basic overview of what this is all about, so that you know that if you have an equation like this, how you set it up. Okay, this is nothing particularly relevant only to a turbulence class. I mean, this could go, you could use this information or knowledge to any equation for that matter. But I am going to use the mean flow equation, which we have derived as per our turbulence class. Okay. So now before I do that, there is yet one more turbulence model I thought one should just sort of at least mention. Okay, briefly what it means, and because this is widely used and it's pretty sort of common, and I have used it as far as my research is concerned as well. Okay, so it's essentially the K omega SST turbulence model, shear stress transport. Okay, so K omega SST turbulence model. What does this mean? Right? Shear stress transport. Right? So what does this mean? Well, what is interesting about this part is that one actually uses both the K omega and the K epsilon equations. Models rather. Okay, so one uses both of these models, but in different zones of your domain, if I were to put it that way, right? So if you have a boundary layer, right, so then close to the wall, right, close to the wall is what you use as the K omega model, and when you're far away from the wall, then you use the K epsilon model. Okay, so we actually use both of these, in tandem. Okay, and so because of that, what is the advantage? Is the solution which is close to the wall, which is near the boundary layer, is integrated without any singularities, and there are really no the solution at the outer wall, where we are sort of going away from the wall, it doesn't suffer from sensitivity to free stream turbulence. Okay, and apart from these, they also use this Bradshaw's condition in the separated region, right? Well, therefore, which is less diffusive, because so we use that condition in the separated region because again that is less diffusive than the K omega model. Okay, so I'm going to write all that down. Okay, so this is obtained by, so this is obtained by blending, okay, k omega close to the wall, k omega model close to the wall, and k epsilon away from the wall. Okay. So essentially then solution is integrated close to the wall without any singularities. Okay. And at the outer wall, it does not suffer due to free stream turbulence sensitivity. Rather, okay. And along with this, separated region, Bradshaw's conditions, right, are used. Okay. Well, let's just say it is less diffusive, okay, than k omega model. Okay, so actually this is almost okay. So what this essentially means that the k omega SST model, turbulence model, is actually solving two extra equations, right? Other than the the ones given by these models. So k omega and k epsilon both are two equation models, right? So apart from these two, it also solves. It involves solving two more equations. Okay. Number of equations okay, so two additional equations, right? Intermittency transport, and momentum right. So momentum thickness based RE, so that's essentially usually denoted by theta, because momentum thickness is denoted by theta, right. So we essentially, the k omega SST turbulence model will also solve these two additional equations. I'm not sort of explaining in detail at this point of time, this is just sort of to give you an overview. Okay, and this is also called, Mentor's turbulence model. So this is all detailed in a paper by okay. All right, so I think that's where that's all. Okay, so that's all I want to talk about. Now let's get on to the CFD part. Okay, so we started out with that, and we said that I wrote out some difference formulas. Let me sort of bring that up. Okay. Yeah, so I think, right, so we had this equation, right? Okay, so I think we'll just have to remember. Okay, so these are the difference equations, difference formula that I had written out. You might be even aware of this. Okay, so the point is that when we say that I'm going to solve a turbulence problem using CFD, just go to answers and press some buttons and get some answers, right? Is that what it is all about? So I think so that's where we are that's the question we're asking. So okay, so how do we actually get around to doing that? What exactly are we doing? Okay, so do it once. I mean, it's a fun exercise. I think you should be interested to play around with it and see how that works. Take a very simple equation and you will see this is interesting. Okay, so essentially what I have here, it's essentially a grid, right? I've just drawn a rectangular grid, and like I said, this is a very basic, simple explanation, right? And CFD has really progressed, much beyond what I'm going to just describe. But to keep things simple and sort of give you the basic idea of what this is all about, right? How do you take that equation and solve it over a grid, for that matter? Okay, all right. So this is a grid. It's essentially a Cartesian grid. Okay, so there is an axis system. There's an x and a y, and you take a rectangular domain and you just draw a grid on it, right? So these distances are delta x and delta y. Typically, they are same. They don't have to be. Right, and each of these these are the nodes. What are these nodes? We are kind of giving them some numbers. Now these are locations where we will calculate our specific values of the variable with which we have written out an equation. Okay, so the point is that why do we have to do that? We're actually going to try and calculate specific values, in the domain. Now, where in the domain? So that's why we take the domain, divide it into, a grid, and everywhere the lines intersect. So that is a grid point, right? So therefore, I call this as I plus 1. This is an I minus 1, I plus 1, so on and so forth, right? So that's what I do. And then what you see here is that if I have a derivative, for example, if I have say I've written, this is a central difference formula, backward difference, forward difference. I'm not going into the details of that. I'm going to just say what the equation means. Now, sorry, the expression means. So if I say f, so f is essentially any function which is a function of x. So this xi essentially means this xi. Now, for example, this I is this one in red here. Okay, this is what I'm showing. So if I have to calculate the derivative of the function f at this xi, right, how do I do that, right? So you'll be like, okay, find out. If it's a sine x, then it's cos x. That's the derivative. If it is cos x, then it is minus sine x, right? Am I right? If it is x squared, it is 2x. The point is, what if I do not have a function like that, and it's just so complicated, and there is no there's no defined function like that? Then how do I calculate that derivative there, right? And that derivative essentially is giving me the change of the property as I move in the fluid domain from one point to the other, and this is important for me to know, right? So then how do I do it? So that's where the CFD comes in, right? So if I had to calculate the first derivative, first order derivative, like dy by dx, that is, right? So in here, so I write that at f. So f is my function, and this is essentially that. So then what I do here is I go here, right, and I calculate is I plus 1. So I take, if it is, if the now the point is derivative is in which direction. If it is in the y direction, so then it is f dash, xi, but in the y direction, that is del y of fx at I, and it could be del x of I as well, right? So in here, when I show these 2 points here, so I plus 1, I must, I can basically get del f del y. Right? That's the first derivative, and if I do that, all I have to do is, first derivative means the function value at I plus 1 minus the function value of I minus 1 divided by the distance between them, which is essentially 2h. Okay. If I need the second order derivative, that is d2 f dy2, say, then I take this value, so y at I plus 1 minus 2 times the y at I plus the value of y at I minus 1, all of that divided by a delta y squared, right, which is what I have written here, right. Instead, now if you had to do a forward difference, so now this is a central difference for differencing, right. You could write the derivatives in this fashion. You could also write the derivatives using these two formulae here. So instead of writing the first order derivative as I plus function values at I plus 1 and I minus 1, I might as well just write this as I plus 1 minus yi by h, right. I could also write this as a function value at yi minus the function value I minus 1 divided by h. I could do that. Or central difference, this the function value at I plus 1 minus I minus 1 by 2h, right. So that's what this means. Okay. So now let us okay. So what I'm going to do is draw up a grid, of course. Okay. Now let me write down the mean momentum equation. What, let us remind ourselves. Okay. So we are going to set this up in a CFD, mode domain. Okay. Now we have a mean momentum equation. Okay. So this is my mean momentum equation, right? And I'm saying I'm going to solve this using CFD, right? The issue is essentially this. So how do I go about doing that, right? How do I go about doing that? Let's do that. So first things first, okay, I'm going to draw up a grid. Okay, this is a representative grid. So let's just say I'm going to do that. So say my grid is something like this. Okay. This. Okay. And then I'm going to say this is 0. Okay. This is 1. this is 2, this is 3, 4, 5, right, 6, 7, 8. So, I am setting up this grid, okay. 9, 10, 11, okay, 12, 14, okay, and then this is your delta x, right, and this your delta y. Okay, all right. So now let's just say, now let us look at this equation here. So I have a, so what do I need here? So why did I talk about the derivatives the way I did just a few minutes back, right? So you see, I have a second order derivative of uj here, and that's, you know, I also have a second order derivative with respect to uj in this form, which is basically in both axes, and also have a derivative of the pressure, right. So that's what we need to calculate now, and I have this domain. How do I do that? What is it that I do here? Okay. All right. So let's just say that this second order derivative, let's look at that. Okay. Let's say del 2, okay, del x2 u. Okay. Now let's decide okay. Now let's decide at which location shall we take this. Let's just say we'll take this at this location, which is 0. Okay. So this one at location 0. Okay. And so in that case, I think I should also sort of write down this axis system. This is y and this is x, right, which is origin is somewhere here, origin is this here. Okay. All right. So then let's just say it is at O, right, the second derivative, right, and this derivative, now this derivative is in the x direction. So this derivative is in the x direction, right, and if I use a central difference formula, we just saw that all we need is the location function value at a point which is ahead of it, right, then minus 2 times the function at the location that you are looking for, plus function value at the location just behind it, okay, by the distance. So this is now the question. Now you could ask here that, okay, so you are, so essentially what I am saying is that I need the derivative of the mean value of the velocity at the location 0, right, and then I am saying that that can actually be figured out, you know, without doing any calculus, but actually just taking the values or individual values of the functions of the mean value at say 0, 3 and 7, and I bunch them up together like this, right, and that gives me the derivative, second order derivative at location 0, right. So you can ask, well, you know, these kind of these you know, these are so far apart, why didn't you take something closer? Yes, you could, right, and how you draw the grid and how close they are, how delta x and delta y affect your thing is a very important study, right. Having said that, beyond a point, decreasing your delta x or delta y is not going to help, and that exactly is your limitation of your numerical method. Okay. Now, here of course, I have drawn this grid really nice and big and large just for just to help our understanding a little better, but really you could have as many divisions as you want, as possible actually for that matter. Okay. So, surely you could make this grid really small and really compact and then use it. Okay. So, that of course that would make it more computationally exhaustive, that you can see. Okay. In other words, I have a domain, the way I have drawn it here, it's kind of pretty spread out, right, and I am looking at the change in a property, which is the mean velocity here, right, at a certain location, and I am using the function values at other locations, but these are locations which are kind of spread out, right. So, I am using those values. Instead, I could do this in a much smaller domain, taking function values in that smaller domain, right. So, I would my accuracy would definitely be better. Yes, but like I said, there is always a limit to that. You can only do as much. Okay, so that is one value. Okay, let's so this is basically the second order derivative, right, of the mean velocity at the location 0. Okay. So, okay. Then next let us go to this one, the second term on the right hand side here. So, let us go to that, and we have something called del 2 del x del y mean value, and let us then calculate this at again the location 0, right. Now, this is nothing, this is say this is equal to del y, okay, right. At O, right, at 0. So, this is a del y of del mu del x, right. So, let us do that. So, this is del y. Okay. Now, derivative, first order derivative of the mean velocity at this location in the x direction. So, if I use central difference formula, it is going to be the function value at a location which is ahead of it minus function value at a location which is behind it by 2 delta x, right. Then this I can then write, so 1 by 2 delta x, right, into del y of this minus del y of u7, right. So, this means first order derivative of the function value at 3, right, at 3 function the first order derivative of the function value at 7. Okay. If I do that, what do I get? This is in the y direction, right. So, again I will use a central difference formula. So, if I use 3, it is 2, right, 2 minus 4, function value is at 2 minus 4 by 2 delta y. Now, let me ask you this. When I wrote u3 minus u7, okay, why didn't I write u7 minus u3? Why didn't I write that? And now I am saying that for example, u3, this is going to be in y direction. So, then I go to a function value which is ahead of it. So, then I am going to write this as u2, right, minus u4, one that is behind it. So, u4, right, by 2 delta y, because I am doing it in the delta y. Now, why is that? Why am I writing, why can't I write y4 minus y2? Well, so simply because I have taken the axis system as such that point you can see that this is positive y, all these are positive, these are all negative, that is why, there is no other reason. Okay. All right, minus again. Now for 7 again, so what is positive? So derivative is basically positive. Okay. So u8 minus u6 by 2 delta y. Yeah. So if you do this, so then this turns out to be 1 by 4 delta x delta y. Okay. u2 plus u6 minus u4 plus u8. Okay. All right. So okay. This, right, and the first one was this. Okay, and we got one more, which is the derivative of the pressure. You know, that should be easy now. Okay, so we can write the if I am going to take it at 0, then this is in x direction. So mean pressure at 3, mean pressure at 7 by 2 delta x. Right. If I do that, then I should be able to now go back and write up the okay, I mean, I have just written out the derivatives, so I should be able to write up the equations. Before I do that, let me finally write out each term, right. So nu into this and all of that. So in this equation 1, so when in the equation 1, I will write out each of these terms. Okay. Then okay. Okay, so that becomes, so essentially what I am saying is, now if I go back, so all I was doing is ddt of at j is equal to 0, right, at this location, and I found out the derivatives, each of these derivatives, right, in terms of function values at various locations, right. Then first term is the second order derivative, which is this one here, multiply that by nu, right. So let me write that then. So that is essentially nu, right, by delta x square. Okay. So if you see, so this is u3 minus 2u naught plus u7, u3 2u naught u7, right, and I multiply that by nu, right, and delta x square was there. So then the next term is nu t into del 2 del x del y. So del 2 del x del y is here, right here, right. I multiply this by nu t, okay. So this one is plus nu t by 4 delta x delta y. Is that right? Okay. And then what we have is u2 plus u6 minus u4 minus u8. Is that right? Okay. And then again, if I go back, the pressure term is essentially at this location is 1 by rho into P3 minus P7. Okay. So minus 1 by rho 2 delta x, right, and this is P3 minus P7. Yeah, so this is one equation. This is essentially one equation. Now, if you see this, if you see here, so if I were to take just this part of the domain, so I essentially have 15 node points, 15 locations in the domain. Those locations are essentially the intersection points of the grid lines, right? And these are the points, I have marked them. So 0 to 14. So 15 points are here where I could potentially figure out the values of the mean velocity, which is this u mean, right? And that would be my solution. So how would I do that? Right. So what I have gone ahead and done is written out this one particular, the change in the velocity, etc., at one location, which is naught, right? And then I find that I'm basically writing out the derivative in terms of function values at various locations in the domain, which is what I've done now. Okay. Now, what is interesting is that momentum is conserved, right? Now, before I sort of go further, so momentum is conserved, right, which means what? Which means that the left hand side of this is actually equal to 0, right, which means in that case what happens to the equation, right? In that case what happens to the equation, so I can just take the pressure terms to the right hand side. So then I can write, you know, at one point, I can write that nu okay, is equal to 1 by this delta x so that is one equation. Okay, interesting. So now having said that, so we're going to, so therefore we can write it now like this. Okay, so let's do that. So let's do that again. Okay, let's write this up for a couple of points, right? So and then essentially what we're going to try and do is write this out in a write this out in a matrix form. Okay, so that, and then you realize what the solution is going to be like. Okay. Okay, so now let us write it out at, say, another location. Okay, so let that be. So okay, so I've got O, right? Let us go ahead and write that at, say, 3 Okay, let that write that at 3 and 7, right, and then we will also write that at these locations 2 and I think 6 maybe we could write that at 6 maybe. Okay, where is 10? Oh, 10 is right here. Okay, so you can write that at 10. Yeah, okay. So let us do that. So we're going to do it at 2. Okay, you have 2 and okay. So essentially, what I'm going to try and do is one is here at 2, which is actually at the reason I'm going to take 2 and take 10 is to show you that now these are on the boundary. Okay, now this is my domain. This is my domain. These are the only points that I'm looking at as of now. Okay, I have defined this domain for myself. Now, if I were to use, for example, a central difference formula, okay, for del y, okay, for the first derivative, say at this location, then I will need a point ahead of it, which I don't have because it's at the boundary. Then what do I do? So as of now, what we will do is we will do a backward difference formula from here, right? You could do that. So similarly here, if I have something here, I could probably use a forward difference formula here when I had to do, for example, del x of the function at 10, right? Because if I have to do a central difference formula, I need a value which is behind it in the x direction. So since I can't do that, I'm going to take a forward difference formula. Okay, so that's why I'm going to take 2 and 10. So we'll get to that in a bit. But let's also do in a sort of, I'm almost kind of repeating myself, let's do it at 3 and 7 as well. So I did something here, let's do it at 3 and 7 also. So I'm not, let us see if we can, write it out without separately going this way. Okay. So then, so d dt of u, right, at 3. Okay, so what I have here is nu into, okay, del x square, okay. Let's go back. So 3. So we will need 13 and naught. So function value at 13 plus function value at 0 minus 2 times the function value at 3. Right? That's the central difference formula. So this is u13 minus 2 u3, okay, plus u naught. This, right, plus okay. So if you see u2, u6, okay, del x, del y here. So in this, okay, u2, u6, u4 and u8, okay. So u2 and u6, right, you add this up and subtract u4 and u8. So now I am here, you add 3, so 12 and 5 I'll add up, subtract 14 and 1, right, these are the diagonal ones. So how am I sort of looking at that? I'm just looking at these values, right, I'm looking at these values. So essentially I'm looking at the diagonal values of this. So then what I get is u12 plus u15, right, minus u14 minus u1, okay, and the pressure term, this is delta x. So this will be 13 minus naught, I think, yeah. This will be my pressure. Okay. Again, since the left hand side is going to be 0, right. So I can actually sort of, let's do that. right. So, basically we are going to say this, right, is equal to this, the right hand side, right. That becomes your equation. So, and I am going to call that as this. Okay. Right. So, now if you go back in here, so look at 7, right. So, let us write that down at the 7 as well. Okay. Okay, and that is equal to, okay. So, if I look at the grid, so 7 is function values at 0, function value at 10, and 2 times the function value at 7. So, use this function value at 10, okay, plus nu t by delta x delta, okay, again 7 and 9, if so it should be 1 and 9 and 5 and 11. So, 1, 9, 5 and 11, okay, minus 1 by 2, this thing, it would be 7 minus naught, 7, oh yeah, well, naught minus 10, yeah, b naught 10, right. So, again the left hand side is 0, okay, again this is 0. So, I have this, right, is this is equal to this, then this is my third equation. Okay. So, the next thing is, like I said, we're going to go and look at two locations at the boundary. Okay. So, one is I think 2 we said, right. So, we will look at, so let us do that. Okay. Then this. Okay, I am going to just write out the basic and then we will stop. Okay. Now, this one, the first one is if you look at the your equation, it is the derivative in x direction, right, x direction, and I am looking at the point 2. So, I need to go, so basically 12 and 1. So, it should not be an issue. So, let us do that. So, it is going to be delta x square, okay, 12 minus 2 u2 and u1. Now, this is the part. So, this nu t, right, nu t into del x del y, okay, of this, okay, minus again P12 right. So, now the issue becomes this part, this is the part, right. Why is this an issue? Because delta x is not a problem, delta x is not a problem. The x bit is not a problem, but when I go in the y direction, when I do in the x direction or in the y direction, then of course I don't have a point ahead of 2 because this is the on the boundary. Then what do I do? Okay. So, I think we will stop there, we will take this up in the next class. Okay. So, we will finish this, we will finish writing this out and setting up the grid, you know, and right. So, we will do that in the next class and we will stop for now. Okay. Thank you.